On problem 617, you have a pendulum, and you give it a kick here, and the initial velocity is 4 meters per second. They give you the length of the pendulum, and the length of the pendulum is 1.8 meters. So I'm converting all of these over to MKS. They tell you that they want to figure out how high it rises, from this lowest position. How high did it rise? You can use the work energy equation to figure this out. If you call this bottom dotted line that I'm drawing here, this bottom dotted line right there, if you let that be h equals 0, the height that you're going to use in the potential energy equation, that means that the initial potential energy is 0. The mgh term would be 0 initially. And since it comes to rest afterwards, you can say that the final kinetic energy is 0. There's also another 0 term, and that would be the work. Remember that the work in this work energy equation is the work done by all forces acting on the object except for gravity, because we account for gravity in the potential energy. If you look at the pendulum bob, there is a tension going in that direction, force of tension, and there's a force of tension going this way. So what about the work done by the force of tension? Well, at every position, the tension is upward, well, not upward, but the tension is in one direction, and the displacement is 90 degrees away from that. Even over here, when the tension is off in that direction, just before it was arriving, it was going in that direction. So at every position along the path of this, well, I guess we can write it symbolically like this, that the force of tension is perpendicular to the displacement. That means that the work done by the tension, if we just focus on that, would be the displacement times the tension times the cosine of the angle between them, which would be 90 degrees. And it's this part of it that is equal to 0. Cosine of 90 is 0. So it's, if you think about it, since this force is perpendicular to the displacement, it can't do any work. You have to have force in the direction of the displacement to do work. Alright, so I kind of got long-winded on that, but you got the idea. You basically have the initial kinetic energy equal to the final potential. 1/2 mv initial squared equals mgh. The masses cancel out, and it gives us that the height that the pendulum rises is equal to v initial squared divided by 2g. They gave you the initial velocity to be 4 meters per second. You know that the acceleration due to gravity is 9.8 meters per second square. That will allow you to find the height. What they also ask you to do is to figure out what this angle is. What is the angle of the pendulum that it makes with the vertical? A little more challenging, but you can make a right triangle out of that. So let me make that right triangle off to the side to make it really clear. Well, I'm not going to make the triangle first. I'll make the arc first. This is length L. That is length L. If I draw my right triangle in there now, then I can say that this length is L minus h, because this is the height that the pendulum bob rose during its motion. So if we're looking for that angle theta, it looks like it can be, well, the cosine of theta would be the adjacent side, which is L minus h over L. And so if you're looking for theta, it is the inverse cosine of 1 minus h over L. That last step you didn't really need to do. You didn't have to divide both terms on top by L. but there it is. So you find h from here, put it right there. They tell you what the length of the string is initially. You can find the angle that the pendulum string makes with respect to the vertical using the inverse cosine.